Alright, in this video we're going to be working some double integrals for multivariable calculus. And so this is before, we don't really have any special techniques of double integrating, no reverse the order, no polar change variables, nothing like that, just regular old-fashioned double integrals. So I'm going to start with number 1. This is the integral from 0 to 1 of the integral from 0 to 2 x plus y dx dy. Okay. I think with these, I'm going to, if it doesn't sketch the region, even if it doesn't ask me to, I'm going to just sketch the region for you so you can see, you know, like kind of what's going on here. Okay, this is where x is running from 0 to 2 and y is running from 0 to 1. So it will be this region right here that we're integrating over. Okay, so we're going to first anti-differentiate with respect to x, and so that would be 1/2 x squared plus x times y, as x runs from 0 up to 2. Okay, and then we're still going to integrate that from 0 to 1 with respect to y. Okay, that's going to become the integral from 0 to 1 of when I plug in x equals 2, I'll have half of 4 plus 2y. Okay, and then when I plug in 0, I'm going to have 2 zeros, so that's not going to contribute anything. So I'm just going to have the integral from 0 to 1 of 2 plus 2y dy. Okay. And then I'm going to find an antiderivative with respect to y. Okay. And then I'm going to plug in y equals 1 and y equals 0, and I'll get 2 plus 1 minus 0 plus 0. Okay, so that's going to be equal to 3. Oh, calculator in the way. We won't be needing that. So number 2. The integral from 0 to pi. 0 to pi. 0 to sine x of 1 plus cosine x dy dx. Okay. So I'm going to sketch that region again. So y is between 0 and sine x. Okay, I know what y equals 0 looks like. Okay, that's this line right here. Oh, pardon me. This is in view. Okay, y equals 0, that's the x-axis. Y equals sine x, and I also know that x needs to go from 0 to pi, so I'm only going to be interested in y equals sine x between 0 and pi. And so 0 pi over 2 pi. Oh, that wasn't the best sketch ever. Okay, but if that's x equals pi, x equals 0. Yeah, we need to squeeze that. Y equals sine x. Okay, then this will be the region I'm integrating on. Okay. And so I'm going to first integrate with respect to y. So that would be y plus y times cosine x, as y goes from 0 up to sine of x. Okay, integrate that from 0 to pi with respect to x. When y equals sine x, I'll have sine x plus sine x cosine x. And then when y is equal to 0, again, I'll have everything zeroed out. So this is going to be the integral from 0 to infinity of sine of x plus sine of x times cosine x. So I'm going to factor out that sine x, and I'll be left with a 1 plus cosine x, and then I'll be set up for a nice u substitution. Okay, dx. Okay, so I'm going to say, okay, I can see what the antiderivative is going to be, but I've been doing a lot of u substitution lately, and maybe you haven't, so maybe I'll just go and carry out all the steps. Okay, I notice here that the derivative of 1 plus cosine x is very close to sine x, close enough that I can do u du. All right, so I'm going to let u equal 1 plus cosine x, so that du is equal to negative sine x dx. Okay, I have reg x dx, so that would be negative du. All right, and then I need to convert my balance from 0 to pi to some kind of u's. When x is equal to 0, u equals 1 plus cosine of 0, that'll be 2. And when x is equal to pi, u equals 1 plus the cosine of pi is negative 1, so 1 minus 1, that's 0. Okay. All right, so now I'm going to be integrating from u equals 0 up to u equals 2 of, all right, this thing in the brackets. I'm going to leave that in the brackets. Okay, we're going to call that u. Sin x dx is negative du, so I'll put the negative here and then du there. But I said 0 to 2, that's not right. It's from 2 to 0, so I'm going to need to fix that. Here's my eraser. Oh no. Yes, that's from 2 to 0, and that's why, okay, that negative and this negativity from integrating backwards, they'll kind of cancel each other out. All right, and that's negative 1/2 of u squared as u runs from 2 to 0, so 0 squared minus 2 squared. So that's negative half of negative 4 is equal to positive 2. All right, number 3. Okay, number 3 is the integral from 0 to 1 of the integral from 0 to x of the square root of 1 minus x squared. 1 minus x squared dy and then dx. All right, so this region is, right, y is between 0 and x is between 0 and 1. All right, well, we know where y equals 0 is. That's right here. Y equals x, we know what that looks like. Okay. And so if y is between 0 and x, it'll be underneath this line, if x is the upper bound. And then x is between 0 and 1, so maybe I'll say 1 is right there. Okay, and then this will be the region I'm integrating on. Okay. All right, so I'm going to start by saying, all right, what's an antiderivative for this with respect to y? Well, it's just going to be y times that, because that's constant with respect to y. So I'll have y times the square root of 1 minus x squared as y runs from 0 up to x. And I'm still integrating that from 0 to 1 with respect to x. Okay, when I plug in x, I'm going to have x times that square root, and that looks promising because I'll be able to use u du there. And then when y equals 0, the whole thing will go away. So this is just going to become the integral from 0 to 1 of x times the square root of 1 minus x squared dx. Yeah, this one's pretty nicely set up for a u du. So I'm going to let u equal 1 minus x squared. Okay. Meaning that du is negative 2x dx. Now, I don't have negative 2x dx, I just have x dx. So I'm going to say, all right, x dx, I'd be dividing both sides by that negative 2. So that's negative half of du. Okay, now I need to convert some bounds. So when x equals 0, that gives me u equals 1 minus 0. And when x equals 1, that gives me u equals 1. That's 0. Okay, so now I am integrating from 1 to 0. I'm going to make that mistake again. On, all right, the square root of u. And then x dx was negative half du, so I'm going to put that negative half here and that du there. And now I'm ready to go. Okay. I can say that that's 2/3 of u to the 3 halves. Okay. So that's negative 1/2. I'm going to factor out the 2/3. And then I'll be left with u to the 3 halves, so that's 0 to the 3 halves minus 1 to the 3 halves, Both of those, I know what those are pretty easily. And so I'll just end up with positive 1/3. Number 4, use geometry to evaluate the integral. All right, this is about to get way easier. Okay, so now we're just going to really be emphasizing on sketching the region of integration. That's why I put these problems on here, is because I want you to be able to sketch the region you're integrating over. All right, and we know that a double integral of just dA, so this is -2 to 3, 1 to 5. A double integral of dA represents just the area, okay? And so I'm going to sketch this region, okay? Now, it doesn't say, am I integrating dx dy or dy dx? I'll tell you it doesn't matter, okay? It's going to end up the same. Maybe I draw it both ways, okay? Assuming dx dy order, okay, that would be x running from 1 to 5 and y running from -2 to 3. Okay, x from 1 to 5. Y running from -2 up to 3. So we put that here. It's a rectangle. And, all right, it's got a width of 4 and a height of 5. So that area here, or that integral that it is representing, is going to be 20. Okay, maybe you didn't believe me. If you did the dy dx order, then y would be running from 1 to 5. And x would be going from -2 up to 3. So it would look a little more like that. Either way, it's going to be, one of the lengths is going to be 4 and the other one's going to be 5, and we're going to have 20 units of area there. Okay, number 5, the integral from 0 to 1 of the integral from -square root of 1 minus y squared to the positive square root of 1 minus y squared of dA. Okay. In this one, I know that it's a dx dy ordering because, well, if I've got the variable here, it's the opposite variable that I'm integrating with respect to. Okay. So it's x equals -square root of 1 minus y squared on the interior integral, so I know it needs to be, dx needs to be on the inside. So it's dx dy. Right. So maybe I'll just kind of approach this differently here. I'm going to say, all right, I know this is x, so x is between that -square root of 1 minus y squared and the positive square root of 1 minus y squared. Okay. While y is between 0 and 1. And, okay, these are sides of a circle centered at the origin with radius 1. Okay, so that's the -square root of 1 minus y squared. That's the left side of a circle. And so, okay, what do I got here? Maybe I'll... All right, the left side of the circle is going to be like that. That's as good as I've got. And then the right side of that circle is going to be, right there. All right. And so x is between these two curves, but y is between 0 and 1. So I know that I'm really only looking at that upper section, right? So I'm just going to erase so that we're not distracted, but it looks like we're going to be distracted by the shadow of, don't even, hold on, I can't even, that's just embarrassing. Okay, I'll use a good high quality eraser. And I've pretty much already ruined it, and it's too late. Right? Well, I tried. Thanks to all the students that have always given me foam erasers as gifts. Okay, now I've got a semicircle. And, well, I know how to find the area of that. Right, we're going to do that. It's going to be 1. If it's a semicircle, it's going to be half of pi r squared. So that's going to equal 1/2 of pi times 1 squared. That's just pi over 2. All right, number 6. Integral from 1 to 3. Integral from 6 minus 2x to 4 dA. Okay, but I know that because I've got an x in here, I'm going to have to start with dy and then dx. And I think I'm going to actually write that in. I'm also going to call this y equals 6 minus 2x and y equals 4. Okay, so I can start by graphing those things. And, all right, 6 minus 2x would start here, and it would intercept at 3. And then, well, that's the lower bound. The upper bound is y equals 4. Okay, we can draw that. Okay. And then x is running from 1 to 3. Is that where they run into each other here at x equals 1, so that kind of makes sense. So this is the region that we're talking about here. And it's going to have a height of 4 and a width of 2. So that area is going to be half of 8, which is going to be 4. Okay. Got one more problem, one more example for you. Oh yeah, this is slightly different, but not really. Okay, find the amount of volume under the graph of f and above region R. So I'm just going to copy this. F of x and y equals 16 minus x squared minus y squared. Okay, and region R, I'll draw it over here. Okay, it looks like it goes to 1 on x, and it goes all the way back to -2. And in y, it goes from 0 to 3. And that's my region here. So I'm going to be integrating, okay, x between -2 and 1. And I feel like with this equation, it does not matter what order we integrate in because of, it's just constants. Y is between 0 and 3, x between -2 and 1, and neither of these would be difficult to integrate. So it doesn't matter. I'm going to say integral from -2 to 1 and 0 to 3, but I just have to make sure of that, right? That 0 to 3 is dy, and then -2 to 1 is dx. Although, with the symmetry in this equation, I don't even know that that would matter. I think you would probably get the same number if you did it wrong. And, well, that's why I wouldn't ask for that type of integrand on, like, the quiz or the test or something. Because I don't want you to be wrong for the wrong reason. That's never good. It's not mathematical. Okay, so we're going to integrate with respect to y first. That'll be 16y minus x squared y minus 1/3 y to the 3. Okay, as y runs from 0 to 3. Okay, luckily when y is 0, I know that will all clear out and I will have nothing there. So I'm going to just plug in there, and then I'll bring in the second integral because it's kind of a lot. Okay, so 16 times 3 is 48 minus 3x squared. That's promising. I like that. Minus 1/3 of 27 is 9. Okay. Okay, minus 0. 48 minus 9. Is that 39? Okay. Okay. So I've got the integral from -2 up to 1 of 39 minus 3x squared dx. Oh yeah, I just made this problem up. Okay, I didn't get it from a textbook. That's why the number is going to be weird. Okay, now I'm going to anti-differentiate, or maybe I'll leave all of this up here and just zoom out and see how that treats us. Yeah, that'll be a lot better. All right, and I can even put that over here. Okay, so an antiderivative for 39 with respect to x is 39x, and then minus x to the 3 as x runs from -2 to 1. All right, so this will be 39 minus 1 to the 3 is 1, minus negative 78, minus negative 8, which would be plus 8. Okay, so that's negative 70. So I'm adding 70 to 38, and I believe that that's 108. But that'll be all for this video. In the next couple of videos, we'll start working on reversing the order of integration, polar change of variables. We're going to take these double integrals a little farther, and then we'll look at some triple integrals. But we'll see that they're all pretty similar. So thanks for watching.